Assalamualaikum warahmatullahi wabarakatuh. Can you hear me? Can you hear me? Okay. Okay, so we continue stiffness method for beam. Okay, I just pick up one beam question. Okay, from online. So this is the question. Determine the stiffness matrix K for the beam using the stiffness method. Use stiffness method to calculate rotation at node 2, D1, and then determine the reaction of the beam Q2, Q3, Q4, Q5, Q6. Okay. Okay, Alhamdulillah, you can now hear my voice. Okay, so degree of freedom is given in the question. Degree of freedom is given. So there are three nodes A, B, C. Joint is node. There are three nodes A, B, C. So in total, there are 6 degree of freedom. Okay, we can see that there are two fixed support at A and C and one roller support at B. So conventionally, if we look at this beam, we have 3, 1, and 3, 7 unknown reaction. 3 at fixed at A, 3 at fixed at C, so another 1 is located at B. Okay, so conventionally we have 7, but we do not have to count. We do not have to count X component. So there are two here. Okay, there are 2, 1, and 2. Okay, we only count 2, 1, and 2. And we have another 1 belong to unconstrained system. Okay, that is rotation. So if we sketch this for unconstrained and constrained, this is unconstrained, constrained. So we have 2 is located at A, and 1 for roller, and another 2. Okay, and okay, 1 Z component is under unconstrained system. So in total there are 6. There are 6, and okay, we label start from unconstrained. We label start from unconstrained 1, 2, 3, 4, 5, 6. So this is how we label this. Okay, so for constraint system means there are unknown reaction. So unknown reaction will be labeled start from 2, 3, 4, 5, 6. And D, we have only D1. Okay, for the unknown. For the unknown. For the unknown, we have D1 under unconstrained system, and we have 5 unknown reaction under constrained system. So looking at this diagram, D1 is rotation. This is B. So rotation at B. rotation at B. Okay, we have Q2. Q2 means Q2 means vertical reaction at B, vertical reaction at B. Q3 is vertical reaction at A. Okay, just look at the label and at the node position. Q4 Z component means moment at A. Okay, Q5 is vertical reaction at C, and Q6 is moment at C. Okay, so all this is called as physical meaning. Okay, all this is called as physical meaning. Physical meaning. Okay, physical meaning of Q2, Q3, Q4, Q5 and Q6 and so on. Okay, so there are two elements. We have element number 1 joining A and B, and we have element number 2 joining B and C. Okay, to calculate okay, we will use Q is equal to KD plus Q naught, because in this question okay, we can see that member AB has UDL. So this UDL we have to distribute it to the nodes. So UDL is member with load, and member cannot carry load, so we have to distribute it to the nodes. Okay, we have to distribute it to the nodes. Okay, so for Q we have 6 value. There are 6 position, 1 2 3 4 5 6. For D we have 6 value. Same, we have 6 position, 4 5 6. And we have Q naught, which we get from Q naught is Q for element 1, Q1 naught, Q2 naught for element 2, Q2 naught. Okay, Q1 naught and Q2 naught. So what is Q1 naught? Q1 naught, okay, Q1 naught is for element, we will have 4 degree of freedom for element. This is Q2 naught. Okay, this is actually special for beam and frame whenever the member has load on top of it. Okay, basically Q naught for beam, Q naught for frame is come from loading that is subjected on the member. For example, member AB or element 1 has UDL, or member BC has point load subjected on the member. So due to that, we have to distribute it to the nodes. So we have to do one by one element. One element consists of 4 positions. 2 at near end node, 2 at far end node. So we have to do like this for beam as well as frame. However, frame has 6 degree of freedom for each element. Okay, this is beam. So beam has 4 degree of freedom per element. Okay. So we have to this one is called as equivalent. Okay, when we do this, so this is actually we analyzing equivalent nodal forces. Nodal forces Q naught. Okay, Q naught. So because in the equation we have Q is equal to KD plus Q naught. When we analyze thrust, K naught is exists whenever the thrust has the effect from temperature changes or fabrication error. But we do not do that yet. Okay, I introduce first the equivalent nodal forces in beam before at the end of the semester when we discuss past exam papers. So I will touch about Q naught in thrust. Basically thrust we only use Q is equal to KD. Okay, Q is nodal forces, D is nodal displacement, K is stiffness matrix for the structure. Okay, but when we analyze beam, when we analyze thrust, we have to consider this equation. We have to include Q naught because beam has always UD a member with load. Frame also have. Okay, so that is why when we analyze beam or frame, we have to consider this Q naught. Okay, what is Q naught? Q naught is equivalent nodal forces. We calculate based on formula. Okay, under fixed end reaction. So in order to recognize this, we just need to look at the element. If the element is subjected to loading on the member. Okay, whether it is UDL, whether it is it is triangular load or point load on the member, so we have to consider the Q naught. Okay, so what is Q naught? How to get Q naught? Q naught is Q1 naught plus Q2 naught depending on how many element in the beam. So this example has two members, two element, member AB and member CD. Member AB is element number 1, so Q1 naught. Member BC is element number 2, Q2 naught. So we have to combine this Q1 naught plus Q2 naught, okay, to get equivalent nodal forces. So everyone have to understand this. Okay, so Q1 and Q2 naught we have to label like what we label in K. Okay, stiffness matrix. So K is stiffness matrix. K also we get from combination of K1 and K2. So what is K1? K1 is element stiffness matrix for member AB. K2 is element stiffness matrix for member BC. Okay, K1 is okay, the arrow for beam, the arrow is always moving towards right direction, and we do not have to put the arrow. And one more thing is in beam we don't have to calculate CX CY. Because in the formula to calculate element stiffness matrix there is no CX, there is no CY. So we will calculate K. Okay, we will calculate K based on EI and L only. EI and L only. This is the formula for element stiffness matrix for beam, where EI will be put outside the matrix, okay, as constant. So we calculate the K value based on the member length only. There is no CX CY. So we just need to calculate based on L. Okay, so go back to this. Okay, so previously and given as well in the question, element number 1 joining node A and node B, so the arrow is moving towards right direction, so for element number 1, near end is 1, so near end is 1, so this is near, this is far for element number 1. So for K we will label as 3 4 2 1, 3 4 2 1. So for element number 1 we have near and node, we have far and node, so the arrow is moving towards right direction. Okay, so we have YZ, Y, we have Y and Z, Y and Z, so the label is 3 4, this is 1, this is 2. Okay, so doesn't matter if you want to put the arrow. So based on this, the K1 is EI. It must be 4 by 4. Because one element we have 2 from near end, another 2 from far end. So total is 4 by 4. And we label this as 3 4 2 1, 3 4 2 1. And we use this label in Q1 node as well. 3 4 2 1. Okay, 3 4 2 1. Okay, when move to element number 2, for element number 2, so we have K, we have element number 2 here, element number 2. So element number 2 consists of near end, node, far end node. So the arrow is moving towards right direction. Okay, we label degree of freedom YZ. Okay, for near end node, it is actually join B. So the label is 2 1 5 6. 2 1 5 6. So based on this, we will get K2. In terms of EI, we get 4 by 4 matrix. 4 by 4 matrix for element stiffness matrix 4 by 4, and we label as 2 1 5 6. 2 1 5 6. Okay, then we combine to get the structure stiffness matrix. Okay, let's do this. Okay, so we will start with K1. For K1, for element 1, the length is 12. The length is 12 meter. Okay, element 1 length is 12 meter. So in the formula, actually we just need to repeat four values. Okay, we will have 12 over L cube. Okay, and we have 6 divided by L square. We have 4 divided by L, and we have 2 divided by L. We have 4 value. Okay, 2 divided by L. So we have 12 divided by L cube, 6 divided by L square, 4 divided by L, and 2 divided by L. Okay, so 12 divided by L cube is, okay, please, can you please calculate for me? The answer, it is 12 divided by L. L is also 12. L cube. L cube. L cube. Twelve divided by L cube. Based on the formula. Based on the formula, okay, it is 12 divided by L cube, 6. 12 divided by L cube. This is 12. This is 6 divided by L square. And then we have 4 divided by L and 2 divided by L. Okay, so we get 12 divided by L cube is equal to 0.0096. Okay. Okay, now please calculate 6 divided by L square. 6 divided by L square. Six divided by L square, please calculate 6. It is 6 divided by L square. 6 divided by L square. 0.0417. 0.0417. 0.0417. Okay, 4 divided by L. 4 divided by L. 4 divided by L. 4 divided by L. 333. 2 divided by L. 2 divided by L. What about 2 divided by L? Zero 0.167. 0.167. Okay, 0.167. So K1 in terms of EI, so we have, okay, we have 0.0069, and then, okay, and then 6. 0.0417, and then we get negative 0.0069, okay, and positive 0.0417. 0.0417. Okay, next value, okay, this one is 4 divided by L. 4 divided by L. 4 divided by L is 0.333. 0.333. Okay, then it is negative. It is negative 0.0417. Okay, then 2, positive 2 divided by L. 2 divided by L is 0.167. 0.167. Next value is 12 over L cube. Okay, it is 0.00969. And negative 0.40417. 0.417, and this one is 4 divided by L. 4 divided by L is 0.333. Okay, so this is K1 in terms of EI, and the label for K1 is 3421. 3421. So label for this is 3421, 3421. Okay, so we move to element number 2. We move to element number 2. Element number 2, if I'm not mistaken, the length is also same. Okay, the length is also same, so I just copy this. Okay, so since the length is also 12 meter, so this is K2, but the label is now changed to for element 2. Okay, the position is 2156. 2156. So this is 2156. 2156. Okay, so we get K2. Okay, now, okay. Okay, now we solve for equivalent element nodal forces Q1 and Q2 naught. Q1 and Q2 naught. Now we move to, okay, this is element 2. Okay, now we move to equivalent nodal forces. Equivalent nodal forces. Equivalent nodal forces. Okay, nodal forces Q naught. Okay, and this we get from Q kecil, Q capital small letter for element. So Q1 naught plus Q2 naught. Okay, for element number 1, okay, this, okay, and for element number 1, again for element 1, for element 1, okay, for element 1, to analyze this, we have to refer to fixed end reaction. Fixed end reaction. So we have to refer to the appendix page 3. Appendix page 3. So this is the, okay, the formula. The formula. So for fixed end reaction, so we have to assume that the both end are fixed, and due to the support, okay, this W have to be balanced. Okay, so balanced by WL over 2. WL over 2, and for the moment it will be acting like this. Okay, like this. Okay, to counter back. Okay, because fixed end reaction is behavior. The formula for moment is WL squared over 12. WL squared over 12. Okay, so move back to this. Move back to this. So we just need to draw, okay, the beam. Okay, the beam. Member AB or element number 1, the loading, the UDL is given as 5 kilonewton per meter and 12 meter length. 5, okay, it is 5 kilonewton per meter and 12 meter length. Okay, so reaction towards this. So we will have the vertical reaction, for this. Okay, it is 5 times 12 divided by 2. 5 WL over 2. 5 times 12, 60. 60 divided by 2. So this is 30 and 30. Okay, and the moment is always acting in these two direction, opposite direction, because of the behavior. Fixed and reaction is behavior. So we calculate based on formula WS squared over 12. WS squared over 12 for the moment, and we get W. What is W? W is 5. Okay, 5. 5. L is 12 times 12. WS squared over 12. So what we get is 60. So we get this one is 60, this one is also 60, but in opposite condition. Okay, so from this, okay, since this is A, B, or 1, 2, okay, and at node 1 and node 2, okay, we have the degree of freedom. Degree of freedom for node 1 and 2 is 3, 3, 4, 2, 1. 3, 4, 2, 1. So we will get Q1 node. Q1 node position is 3, 4, 2, 1. Then we have to compare. Okay, look at this diagram. Okay, at position 3, okay, it is 30 positive. So this is 30. Okay, for position 4, it is moment at A. Position 4, it is moment at A, and the moment and the component of 4, okay, is same. So it is positive 60. Okay, and then we move to 2. At position 2, the value is 30. We just need to compare these two. 30. And for moment at B, the 60 opposite with the Z component of DOF 1. So it is negative. Okay, this is for element number 1. And for element number 2, since since there is no loading on the member, so for element 2, this time is Q2 naught 0, 0, 0, 0. Okay, so this is 2156. Okay, we get 0 because there is no loads on member. Okay, no load on member, so we get all 0. So we combine this, we will get, okay, when we combine this, so we get Q naught, which is equal to 1, 2, 3, 4, 5, 6. So 1 is negative 60, 2 is 30, 3 is 30, 4 is 60, and 5, 6, 0, 0. Okay, so now the next step, we want to calculate unknown displacement. We want to calculate unknown displacement, so we want to write the force displacement equation. Force displacement equation or stiffness equation. Okay, stiffness equation. So this is Q is equal to KD plus Q naught. Okay. Q is equal to KD plus Q naught. And when we want to solve for the unknown displacement, to solve unknown displacement, we need to consider unconstrained degree of freedom system only unless when there is a support settlement. Okay, means that if in a question there is no question mentioning about writing stiffness equation in full or writing force displacement equation in full. Okay, read the question carefully. If in the question mention question C, for example, write the stiffness equation full stop. Write the stiffness equation full stop means you have to write the stiffness equation in full 6 by 6 matrix. But if in the question is just determine K, establish K, and then solve for the unknown displacement, and then solve for the unknown reaction, then actually we don't have to write in full. Okay. Okay, to get in full, actually to solve this, we just need to consider one equation because of one unknown. Means that we will produce, okay, Q is equal to K, this is K, EI, this is D1 plus Q naught. So Q naught is this at position 1. Okay, Q, okay, go back to the question, Q. Okay, Q1 means rotation, Q1 means moment at node 2. Q1 means moment at B. And from the question there is no moment. Means that the value is 0. So here is 0. Okay, EI means 1 position. K is 1 position. So for 1 position it is 0.333 plus 0.333. 1 position. Okay, it is 0.666. So here is 0.666. Okay, and Q naught is negative 60. So this is actually the equation to solve for the unknown displacement. When we rearrange this, so what we get is, okay, let's say EI is 200 GPa, I is 506 mm4. Okay, so we have to convert EI equal to 200 times 10 power of 6 kilopascal. Kilopascal because Pascal is kilo Newton per meter square. Okay, and we have to times with 500 times 10 power of 6 times 10 power of milli, negative 3 times 4. It is negative 12, so meter 4. So cancel 6 plus 6 minus 12. 6 plus 6 minus 12. So what we get is 200 times 500 times 10 power of 0. So that is why we get this as 200 times 500 only, and it is 100,000. 1, 2, 3, 4, 1, 2, 3, 4, 10. Okay, so the unit is in kilonewton meter square. Okay, kilonewton meter square because this and this, okay, we get meter square. So the unit for EI. So when we substitute into this equation, okay, into this equation, stiffness equation, so we will solve. So what we get is, okay, ni, okay, what we get is, it is 200 times 500, 100,000. Okay, it is 100,000, okay, times 0.666 D1 equal to 60. Equal to 60. So we get D1 is equal to 60 divided by 100,000 times 0.666. So what is the answer? So this is D1. D1. If only one unknown displacement, and in the question not mentioned about writing stiffness equation in full, so just do like this. Okay, 60 divided by 100,000 over 0 divided by 100,000 times 0.666. What is the answer? What is the answer? Please calculate for me. Zero point zero 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 nine. Zero 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 nine. Power negative 4. Okay, positive, yeah. So it is 0.0009. So this is in radian. So this is the rotation. So D1 means this D1 means rotation at support B. Rotation at support B. Okay. Okay, now we want to continue to calculate Q2. For example, reaction. Reaction at Q2. Okay, Q2 is reaction, vertical reaction at B. Q2 is vertical reaction at B. Vertical reaction at B means, so if we have the matrix D plus Q naught. Okay, so all these labeled as 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 3, 4, 5, 6. And we have D1. D1 is now 0.0009. Okay, 0.0009. We want to calculate Q2. Q2 here. Okay, Q2 means we have to consider this line number 2, times all this. However, the rest of means D2 until D2 until D6. So all 0, 0, 20, 30, 40, 50, 60. Okay, and then we have to plus this value. The value is 30. The value is 30. Okay, so only one value here, okay, will give us value. We give us the answer. So Q2 is equal to EI. So this is position, this is 2, 1. The position is 2, 1. 2, 1 EI, 2, 1. So we get 2, 1 from K1 and K2. 2, 1. So 2, 1 is 1, 2, 2, 1 is the same. 1, 2, 2, 1 is the same. So we have here negative 0.0, negative 0.0417 and 2, 1 from K2. Okay, 0.0, 0.0417, 1 positive, 1 negative. So the answer is 0. Okay, so this one 0. But we have to plus with, so this is 0 times 0.0009. We plus with 30. So Q2 is 30 kilonewton. Okay, that is actually the mathematical process in the stiffness equation that we should do like this. Okay, so basically if in the question there is no question mentioning about writing in full stiffness equation, actually this okay, you can imagine, but if you cannot imagine, you have to write in full. Okay, you have to write in full. So this is Q2. Okay, let's do another one. Let's calculate Q3. Q3 means Q3, this is Q3. Line number 3 times this displacement plus Q naught at position 3. Q naught at position 3. And Q naught at position 3 is 30. So this is 30 as well. 30, this is 30. Okay, we want to have the value at position 3, 1. 3, 1. Because only 3, 1 will give us value 3, 1. 3, 2, until 3,6 will give us 0. Okay, 3,1, position 3,1 means find the value from K1 and K2. Okay, 3,1, we have 3,1, 0.00417. 0.0417. So for the mathematical equation, EI, it is 0.0417 times 0.0009. Okay, plus with 30. Okay, EI, actually if we don't, doesn't matter if we do not divide the displacement divide by EI, because EI will be cancelled if D is in terms of EI. But if like this, so we have to times back with EI value. So what is the answer? EI 100,000 times 0.0417 times 0.0009 plus 30 Q3, and Q3 is also vertical force. Okay, please calculate for me. EI 100,000 times 0.0417 times 0.0009 plus 30. 33,753. So it is 33,753 kilonewton. Okay? Okay, now continue Q4. Q4 means 4,1, and Q naught is 60. This one is 60. Okay, means that we have to find the value at position 4,1. At position 4,1, find the value from K1 and K2. 4,1 we can find in K1. 4,1 is 0.167. 4,1 is 0.167. 0.167 times 0.0009. This is 6. Okay, plus 60. Okay, please calculate 100,000 times 0.167 times 0.0009 plus 60. What is the answer? What is the answer? 75.03. 75.03 kilonewton. Q4 is moment, kilonewton meter. Okay, let's look at back to this. 4 is moment, kilonewton meter. It is 70 kilonewton meter. 75.03 kilonewton meter. Okay, so continue to calculate Q5. Q5 is EI. Okay, the position Q5, position is 5, 1, 5, 1. So 5, 1, the value is, the value for 5, 1, 5, 1, 1, 5. Negative 0.0417. Negative 0.0417. Okay, negative 0.0417. 0.0009. Okay, plus 0. So what is the answer? What is the answer? Q5. Q5 is vertical reaction. Vertical reaction EI 100,000. 100,000 times negative 0.0417 times 0.0009 plus 0. The answer is negative 3.753. This is kilonewton. Kilonewton vertical reaction at C. And last value Q6. Q6 EI. So this is Q6. This is 6, 1. Okay, find the value at position 6, 1. Find the value at position 6, 1. 6, 1 is 0.167. 0.167. 6116 is the same. 0.167. Okay, this is 0.167 times 0.0009 plus 0. So what is the answer? 100,000 times 0.167 times 0.009 plus 0. 15. It is 15.03. This is moment kilonewton meter. Okay, so we have got all. Okay, the reaction at the support. Okay, then with this unknown reaction, okay, we can continue to draw the shear force and bending moment diagram. Okay, let's do it. Okay, so this is the beam. Okay, Q2 is roller 30. Q3 is 33753. 33753. Okay. Moment positive is counterclockwise. Positive is counterclockwise because of the sign convention. So 75, it is 75.03 Q4, Q4, 34. Okay, 5 is negative 3.753 and moment is counterclockwise 15.03. UDL 5 kilonewton per meter. Okay, the length is 12 meter. Okay, now we want to draw the shear force diagram and bending moment diagram. Okay, for shear force diagram, Okay, so it is positive 33. Positive 33.753 means it is going to be like this. Okay, we just need to follow the arrow. We just need to follow the arrow going up. Going up, and the value is 33.753. 33.753. Okay, now this 33.753, because of the 5 kilonewton UDL, so we have to minus by 5 times 12. Okay, so the process is 33.753. For the next value, we have to minus by 5 times 12. Okay, this is the second step. The second step. 33.753 minus 5 times 12. We just need to follow whatever whatever vertical forces that exist in the beam. Okay, start from positive 33. Start from 0 plus 33.753. Okay, the first one is 0. We plus because of the arrow, plus 33.753. So we get 33.753. Then we use this value here. We minus by the UDL, 5 times 12. So what do you get? 33.753 minus 5 times 12. What do you get? 33.753 minus 60. Okay, please calculate. 33.753 minus 60. We get negative 26.247. Negative 26.247. So it is negative. Okay, the point is, okay, so let's say this is negative 26.247. Negative 26.247. So we get this as negative 26.247. Okay, the third step. Okay, continue. Negative 26.247. Okay. Next value, we have to plus with positive 30. Plus positive 30 plus 30. So what do you get? Plus 30. Negative 26.247. We have to plus 30 for the next point. For the next point. So 3.753. It is positive at positive side. At positive side, okay, let's say here this is 3.753. Okay, positive 3.753. Okay, so next step number 4. So use back this 3.753 we have to minus by 3.753. So minus by minus 3.753, we get 0. Okay, we get 0. That is the process to draw the shear force diagram. Okay, in the shear force diagram, okay, start and end must be 0. So sini start, sini end. Okay, end at 0. So this okay, somewhere here 3.753, this one is 0. Okay, so the shear force diagram should be look like this. Start at 0. Okay, start at 0, go up, and then down, and then up, and then go straight, and then down. Okay, so this is the shear force diagram. Positive, negative, positive. Okay, positive, negative, positive. So this is shear force diagram. Shear force diagram. Shear force diagram. Okay, now using shear force diagram, we will continue to draw the bending moment diagram. Bending moment we get from the area of shear force diagram. When there is an intersection like this, okay, intersection means maximum moment. Maximum moment in bending moment diagram. Intersection means that we have to determine the distance from, okay, from A to the intersection. From A to the intersection. Okay, so how to get this? So this value will be equal to, okay, this value will be equal to 33.753 divided by 5. Okay, we get from kilonewton per meter to get meter. Okay, so please calculate what is the answer. It is 33.753 divided by UDL. UDL is 5. So 33753 divided by 5. 33.753 divided by 5. What is the answer? 6.75. So this is 6.75 meter. 6.75 meter. So the remaining 12 minus 6.75, 12 minus 6.75. It is 5.25. Is it? 5.25? Okay, 5.25. Okay. Because we have to determine this. We have to determine this because we need the area of this triangular. We need the area of this triangular in determining the moment. Okay, now we want to draw the bending moment diagram. Okay, first I want to draw the dotted line, draw the line. Okay. Then the intersection. Okay, then at position B, then at position C. Okay, so now draw a horizontal line. Okay, moment at A is negative, is counterclockwise 75.03. 75.03. Okay, when writing bending moment diagram, doesn't matter if you want to put positive upward or negative upward. But for analysis, but for design purpose, you have to draw negative upward, negative here. This is negative, this is positive for design purpose. Okay, so this is negative. Okay, counterclockwise. When draw the diagram, this is counterclockwise, means negative. So we put at negative side. It is 75.03. 75.03. 75.03. We have to plus with the area of the triangular. Okay, always start at 0. Always start at 0. So this time, so it is 0, 0. We minus by number 1, 0. We minus by 75.03. So we get negative 75.03. Okay, now we don't have to follow sign convention for stiffness because this is general one. Draw the bending moment diagram when we have all reaction in the diagram. Okay, so it is 0 minus 75.03. We get negative. So negative we put okay here. And we have to, okay, step number 2. Step number 2, it is negative 75.03. We have to plus the area. We have to plus the area of this triangular. Okay, so we have to plus 1/2. The distance is 6.75. Okay, the moment, the force is 33.753. 33.753. 33.753. Then, okay, please calculate negative 75.03 plus area of triangular. Half times 6.75. 6.75 times 33.753. What is the answer? What is the answer? 38.89. So this is 38.89 positive. So all this is moment 38.89 positive. So means that we have to draw at positive side 38.89 or 86 or 87. Okay, 89. Another answer? Another answer? 38.89 or 38.87? Another answer? This one? Negative 75.03 plus half times 88689. Okay. Okay, next value, the third step. The third step to draw the bending moment diagram, the third step is 38.89. Okay, we have to minus the area of triangular. Okay, it is minus 1/2 5.25 times with 26.247. 26.247. Okay, please calculate 38.89 minus half times 5.25 times 26.247. What is the answer? What is the answer? Negative 30.01. Negative 30.01. So all this moment. Negative 30.01. Okay, negative 30. So now negative 30.01. Okay, 30.01. Okay, 30.01 we have to plus. We have to plus the rectangular. Negative 30.01 plus the area of rectangular. Okay, means that here the next step is for it is negative 30.01. We have to plus, it is 12 for the length and 3.753. 3.753. Okay, what do you get? Negative 30.01 plus 12.3. 12 times 3.753. it should be 15. 15.03. 15.03. So this is 15.03 kilonewton. 15.03 kilonewton. It is positive. Okay, it is positive. Positive. Okay, positive. It is 15.03 positive. Okay, and the last point will be this. Okay, so this one is negative. This is negative. This is negative. Okay, means that when we get this 15.03, this 15.03 is positive value. Positive value 15.03. Remember, the diagram must be closed at 0. So the last step is 15.03. We minus by 15.03, we get 0. Means that this is the end point. So this is the end point. Okay, this is the start point. Okay, so the last point is 0. 0. So for the diagram, okay, for the diagram, okay, and because of UDL, so this one we have like this. Okay, so all this negative, negative, positive, positive. Okay, so this is how we draw the shear force diagram and the bending moment diagram in full. Okay, actually in analysis, the end product is, for beam analysis, the end product is whenever we can draw the bending moment diagram before we continue further to do design. Okay, it will relate dengan design lah. After this you will actually use this information that we get from the bending moment diagram to start design. Okay, so this is the bending moment diagram and shear force diagram. Is it okay? Is it good? Is it okay? Is it okay, everyone? Do you have any question to ask? If you have question, you can write. Okay, I have put all the step to the step for drawing the shear force diagram and bending moment diagram. Okay, it's written here. So this is for the shear force diagram step, yeah. Okay, shear force diagram step, and this is for bending moment diagram steps. Okay, so this example I do it quite detailed. Okay, start from uh, of course start from dividing the beam into element, and we have to label degree of freedom. So degree of freedom we label based on unconstrained and constrained system. Okay, so anyway you have to always need you need to always refer to the question given, because this question, if we look at back to this question, the question asking you to establish K and then D and then force. Okay, so you just need to read the question. So in this question you have to actually the stiffness matrix K, capital K, this one you have to give in full K. If the question just asking these two questions, okay, asking these two questions, one calculate displacement and another one calculate reaction, you can actually follow the step I have shown to you tonight. Okay, anyway you have to refer to the question. Sometimes the question asking you to give K in full, sometimes the question doesn't ask you to give K in full but give equation in full. Okay, sometimes there is no question asking you about K and stiffness equation, but in the question stated that you have to use stiffness equation, stiffness matrix to analyze unknown displacement and unknown reaction. Then at that time you can follow whatever we have done tonight. Okay, just okay, means that you just need to understand it very well, all the term, all the physical meaning, labeling must be correct. Okay, labeling must be correct. Okay, you have to know the physical meaning. So we should know that in order to solve for the unknown displacement and reaction, we will use the stiffness equation. So in beam, because of because in beam normally the member, the element is subjected by loading, so we have to distribute the loading to nodes, because member or element cannot carry load, we have to distribute it to the node. And when we distribute the member loading, it is called as equivalent nodal forces. Equivalent nodal forces. Okay, equivalent nodal forces. And the label for equivalent nodal forces same as what we label in K1 and K2. Okay, so we give K1 and K2, and then we analyze Q1 node and Q2 node, and then okay, we solve the unknown displacement by solving solving stiffness equation corresponding to unconstrained degree of freedom system only, because this question has only one unknown displacement. That is why we get only one equation. Okay, one equation like this. Okay, this I have also shown how we change the unit of E and I. Okay, so that is why normally the 200 and 500, we normally consider EI as 200 and 500 only, because of the the exponential 10 power of 6, 10 power of 6 and 10 power of negative 12. We get 10 power of 0 and 10 power of 0 equivalent to 1. This is basic mathematics that you have learned in school. Okay, and then solve this. Okay, this one means you have to recall back what you have learned previously under mathematics course. Okay, this is just a simple matrix formulation calculation. So this is the mathematical calculation. Okay, and then all this give us the beam in full. Okay, so when we have this to get this beam, of course we can also use flexibility method. That is why when we have this, when we draw the shear force diagram and bending moment diagram, Okay, we will back to the original or the standard sign convention. Okay, negative, positive. Okay, that's all. That's all for tonight. So thank you very much. So I hope this will help you a lot. Okay, inshallah we will continue. We will continue one frame example. We will continue one frame example. One frame example by next week. By next week, we will do one frame example. Okay, I will give you one formative assessment. I will give you one question for you to do and to submit for this week activity. For this week activity, so you can watch this video, okay, and try to do it on your own and submit. Okay, I will give you later lah, maybe tomorrow or maybe tomorrow, Thursday. Tengoklah, or Friday. Okay, because tomorrow morning and Thursday I will be in Dewan Besar. Okay, thank you very much. Thank you for joining. Thank you for staying until the end. So we will meet again in another session. Okay, Assalamualaikum warahmatullahi wabarakatuh. Good night.